Hi, welcome to this lecture of two-phase flow. My name is Minchang. I'm currently a faculty at the Department of Power Mechanical Engineering in National Tsinghua University. Per the request from the university, I'm recording and sharing this series of lecturing for NTHU OpenCourseware. The topic of this lecture is conservation of mass, momentum, and energy at the liquid-vapor interfaces. The content of this lecture material is based on the book Liquid-Vapor Phase Change Phenomena, authored by Professor Carey. This figure shows a control volume across a liquid-vapor interface. Recall that in previous lectures, we have shown that there is a finite thickness of the interface, and the analytical methods for determining the thickness with respect to the thermodynamic state and the properties of the fluid. Here, it is assumed that the thickness of the control volume is thin enough so that the accumulation of mass within it is negligible. Also, only the mass flow in the direction of the unit vector normal to the interface, the n direction noted on the figure, is considered. Note that the move of the interface and the control volume is represented by dz dt. This velocity is in general different from the velocities for liquid and vapor phases in the normal direction, respectively. From the conservation of mass of this control volume, equation 1 can be derived. Rearranging equation 1, equation 2 can be obtained. The left-hand side of equation 2 denotes the net mass flow rate into the thin control volume of the moving interface, and the right-hand side of equation 2 denotes the net mass flow rate out from the control volume of the moving interface. This figure shows the transport of momentum normal to the interface with the same control volume. The interface is moving in the n direction with a speed of dz dt. Momentum in the direction of the unit normal vector n is convected into the control volume at the relative velocity of the fluid with respect to the interface. This is represented in the last two terms in equation 3. The pressure difference on the left-hand side of equation 3 denotes the force acting on the interface in the normal vector direction from pressure on both sides of the control volume. The first term on the right-hand side is the surface tension effect. If the motion of the interface is very small due to the limitation of heat transfer, the convective terms on the right-hand side of equation 3 could be negligible. It can be shown that, in this case, equation 3 is then reduced to Young-Laplace equation. This figure indicates the momentum balance in the direction tangent to the interface. The direction denotes with the unit vector s. Referring to the mass conservation, the net mass flow rate into and from the interfacial control volume are used to define the convective flow of momentum in the direction of the unit vector s. The terms in the first bracket of the equation on the left-hand side are the shear stresses at the interface. The second term represents the change on the surface tension along the interface. Assuming that on the interface there is no slip between the liquid and the vapor phases, WLS equals WVS, and assuming that there is no variation of surface tension on the interface, partial sigma partial s equals 0. Equation 5 will reduce to a simple balance of the shear stresses on the interface. Note that the result of mass conservation, equation 2, was used in this derivation. Then, following the definition of the shear stress for Newtonian fluid, which means that the viscosity is constant, equation 8 can be obtained for the momentum equation in the direction tangent to the interface. This figure on the left shows the conservation of energy of the thin control volume across the liquid-vapor interface. Notice that both the fluid enthalpy and the kinetic energy of the fluid are considered. H is the enthalpy of the fluid. Equations 9a and b show the definitions of the speed for vapor and liquid respectively. The first term in the square root is the velocity of the fluid in the direction normal to the interface, the n direction, as we have seen in previous slides. The other two terms are the velocities in the direction tangent to the interface. S1 and S2 denote the two principal radii of the interfacial surface between liquid and vapor. Figure 2.1 is attached here for reference. Equation 10 shows the conservation of energy derived on the basis of Figure 3. By substituting equations 1 and 9, equation 10 can be rearranged to equation 11. It was assumed the interface is at local thermodynamic equilibrium, so the difference on the enthalpy between the liquid and the vapor phases is replaced with the latent heat of the fluid. For many systems, the contribution of fluid kinetic energy to the energy balance is negligible comparing to the change of thermal energy due to phase change. In this case, the factor in the square brackets in equation 11 is close to 1. Also, for a pure substance, if the curvature of the interface is small, the capillary pressure difference is small across the interface. Therefore, PL equals PV, and the temperature in the interface should be the saturation temperature corresponds to the value of pressure on the interface. Furthermore, if we assume that the heat transfer across the boundaries of the control volume is mainly contributed by conduction, by applying the Fourier's law, equation 11 can be rearranged to equation 13. It is worthwhile of noting that if the velocity of the liquid surface is assumed to be equal to the moving velocity of the interface, the right-hand side of equation 13 becomes 0. This leads to the loss of information of phase change in the energy conservation equation, which is apparently not reasonable. Therefore, WLN does not equal to the velocity of the moving interface. According to the equation of conservation of mass, WVN shall also not equal to dZi dt. Here, let's summarize this section. We derived a set of equations from the conservation of mass, momentum, and energy across the interface of liquid and vapor. There are at least 8 unknowns. Therefore, to use this set of equations for analyzing the transport phenomena across the interface, additional assumptions, relations, or measurement data will be required. This macroscopic model could be used in conjunction with the microscopic analysis of the interfacial region that were illustrated in previous lectures, especially lectures 1 and 2, for a complete analysis of the dynamics of the liquid-vapor interface. The vaporization and condensation can provide high heat fluxes across the liquid-to-vapor interface with relatively low temperature differences. What is the highest possible heat flux in a given phase change process? This question will be answered by considering the molecular motion at the liquid-to-vapor interface. From the kinetic theory of gases, the Maxwell velocity distribution for gas molecule motion was derived as equation 121. In this equation, N is the total number of molecules in the system under consideration. m is the mass of one molecule, Kb is the Boltzmann constant, and T is the temperature. The left side of the equation is the fraction of the total number of molecules n with velocities in the ranges u to u plus du, v to v plus dv, and w to w plus dw, respectively. With these velocity distributions for molecules, the relation for the total rate at which molecules pass through a unit surface on the liquid to vapor interface can be derived as in equation 127. Capital M bar is the molecular weight of the vapor. R bar is the universal gas constant. P is pressure. To continue this derivation, it will also be needed to estimate the fraction of the molecules crossing the interface and not reflected. Sigma E is due to evaporation and sigma C is due to condensation. Theoretically, sigma E equals sigma C if no phase change happens on the interface, but this is often assumed to be true even if phase change happens on the interface. This sigma is called the accommodation coefficient. In consequence, the net mass flux to or from the interface can be obtained from the molar flux, the molecular weight, and the accommodation coefficient, as shown by equation 135. The net heat flux across the interface due to evaporation or condensation equals the net mass flux multiplied by the latent heat. Equation 144 is then obtained. The interfacial resistance of heat transfer is defined as the heat flux divided by the temperature difference between the liquid and the vapor phases. It should be noted that for applying this relation, the temperature difference between the liquid and the vapor phases could be small but non-zero. Also noted that equation 144 is an implicit expression since some parameters on the right side of the equation are dependent on the heat flux. A simplified explicit equation is suggested for approximation. Example 4.5 in the textbook illustrates the procedure of using the analysis we just introduced to estimate the interfacial resistance in heat transfer on the liquid to vapor interface during a phase change process. The amount of heat transfer being contributed from evaporation is approximately 3 orders of magnitude higher than that from heat conduction across the interface.